Everybody, in this lecture let us discuss about double refraction as well as Huygens theory for double refraction, right? So now the physical properties of refraction for isotropic medium are same in all directions. The physical properties for isotropic medium are same in all directions, alright, and that of anisotropic substances are different in all directions, right? Now crystals such as calcite, quartz, tourmaline are well-known isotropic substances. Isotropic substances. They have their physical properties same in all directions. So now, in some 1869, Reshma Bartholinus, he discovered that when a ray of ordinary light, that is, we call it as unpolarized light, passes through calcite crystal, it splits into two refracted rays. First one, second one. So when unpolarized or ordinary light passes through calcite crystal, a isotropic substance, it splits into two refracted rays. Okay, the first refracted ray obeys ordinary laws of refraction. Okay, the first point. And the second point is that they have their vibrations perpendicular to the principal section. And such rays which obeys the ordinary laws of refraction and whose vibrations are perpendicular to the principal section of the crystal, we call it as ordinary rays. Okay, we call it as ordinary rays. In shortcut we call O-ray, ordinary rays. Similarly, the second refracted rays, they does not obey the ordinary laws of refraction. And their vibrations are within principal section of crystal. So such rays which does not obey the ordinary laws of refraction and whose vibrations are within the principal section of crystal, we call it as extraordinary rays. In shortcut we call it as E-ray. Okay, E for extraordinary. Okay, so now this phenomena where the refracted rays splits into two refracted rays, we call it as double refraction. This phenomena we call it as double refraction. And crystals such as calcite which exhibits this double refraction phenomena, we call it as doubly refracted crystals. We call them as doubly refracted crystals. So here there are two types of doubly refracted crystals, right? One we call it as uniaxial crystals. Other we call it as biaxial crystals. In uniaxial crystals means that crystals which consist of only one optic axis. Biaxial crystal means that crystals which consist of two optic axis. So do you know what is optic axis? The largest axis in crystal, the largest angle in the crystal, we call it as optic axis, and this optic axis passes through the corner. Okay, a line passing through any of the blunt corners and making equal angles with three faces of crystal which meet at the corner locate the direction of optic axis. Right? So now here let us see what happens in uniaxial crystal. So in uniaxial crystals there is only one direction. One optic axis means what? One direction. So now here, as there is one direction, the two refracted rays travel with same velocity. Ordinary and extraordinary rays travel with the same velocity. And examples for this uniaxial crystals are calcite, tourmaline, quartz. Calcite, tourmaline, quartz. In biaxial crystal, the rays will have two directions. Right? Two optic axes. Now they travel with different velocities. Okay, and the example for these are topaz, aragonite, etc. are the examples for this. Okay, now even at home also we can see this phenomena of double refraction. How means? Let us take a white paper. Okay, this is white drawing sheet or white paper. Now mark a ink dot on that paper. Now place a calcite crystal on that ink dot. Now place calcite crystal on ink dot. You will find two images. When you observe this from the top of the calcite crystal, you will find two images. One image remains constant. We call it as stationary image. Other image rotates around that stationary image. This is rotating image. So two images of ink dot are observed. One is stationary image, other image rotates around that stationary image. Right? So this stationary image so here we are rotating the crystal, right? And while rotating, if we see these two images. Okay, the stationary image we call it as ordinary image, while the rotating image we call it as extraordinary image. Ordinary image is formed due to ordinary rays. Extraordinary image is formed due to extraordinary rays. Similarly, now let us take a calcite crystal, right? Now this is the polarized light. Now let this be the normal drawn. Okay. Now when it enters into the calcite crystal, it resolves or splits. It splits into two refracted rays. Okay. One ray is traveling along BC. We call it as extraordinary rays. Later it be making an angle R2 with the normal. Other is BD. We call it as ordinary ray. It makes an angle R1 with the normal, right? As these two surfaces are parallel, the rays emitted are also parallel to each other, right? Now let us write the refractive indices of these two rays. First, for ordinary ray, mu naught, sin I by sin R, no? Sin I by ordinary ray is making R1 angle, refracted angle. Similarly, for extraordinary ray, mu E equal to sin I by, it is making R2 is the refracted angle for that ray. So, if we take the case of calcite crystal, mu naught will be greater than mu E. Okay, because R1 is less than R2, right? R1 is less than R2. From the diagram itself only we are understanding R1 is less than R2. As these are inversely proportional, what happens? Mu naught will be greater than mu E. Mu E is inversely proportional to sin R, we wrote no here. So, when R1 is less than R2, mu naught will be greater than mu E. So, the velocity for ordinary ray inside the crystal will be less than velocity of extraordinary ray. Right? So, and the next thing we have to observe is that only as velocity of ordinary ray is less than velocity of extraordinary ray, and at the same time mu naught is same for all angles of incidence, while mu E changes with angle of incidence. Okay, mu naught is same for all angle of incidences, while mu E changes with angle of incidence. So only as mu naught is same for all angle of incidences, the ordinary ray travels with the same velocity in all directions, and extraordinary ray, as it changes with angle of incidence, it travels with different velocities in different directions. Different velocities in different directions. So this is about the double refraction phenomena. Now let us move for Huygens theory of double refraction. Huygens theory of double refraction. So what is Huygens theory? So according to Huygens theory, wavefront means what? The locus of all points vibrating in same phase. Huygens principle says that again this each point on the wavefront give rise to the secondary wavelets, or is the secondary source which give rise to the secondary wavelets. This is the Huygens principle, right? So according to Huygens principle, the each and every point on the wavefront give rise to the secondary wavelets, right? Now, so Huygens, he did the experiment on uniaxial crystals. Uniaxial crystals, quartz, tourmaline, calcite, which is having one optic axis. Now he found that he just applied his theory to these secondary wavelets. He found that, or according to his theory, when a wavefront strikes the doubly refracted, when wavefront strikes the doubly refracted crystal, every point on crystal becomes the source of two wavefronts. So means every point becomes the source of two wavefronts, secondary wavefronts. Every point, it becomes the source of two secondary wavefronts, right? Now, the first wavefront, or one of the wavefront, we call it as ordinary wavefront. Other we call it as extraordinary wavefront, right? Ordinary wavefront, it corresponds to ordinary rays. Extraordinary wavefront corresponds to extraordinary rays. Okay. Now, as it corresponds to ordinary rays, now only we said that ordinary rays, the refractive index of ordinary rays remains the same for angle of incidence. So, the velocity will be same. Velocity of ordinary wavefronts, okay, or ordinary rays which generates ordinary wavefront will be same in all directions. So only it takes spherical shape. We call it as spherical wavefront. And extraordinary rays, extraordinary wavefront is produced due to extraordinary rays, and the velocity is different in different directions. So the shape of this extraordinary wavefront will be ellipsoid. Will be ellipsoid, means in the shape of ellipse, with optic axis as axis of revolution. With the optic axis as axis of revolution. This is the first point he said. Now the second point what he said means, this sphere and this ellipse touch each other. Spherical wavefront and ellipsoid. Ellipse touch each other at points which lie on optic axis. So if this is the optic axis, sphere and ellipsoid touch each other at the point which lie on the optic axis, and at this position the velocity of ordinary ray will be equal to the velocity of extraordinary ray, or both velocities are same along the optic axis. Both velocities are same along the optic axis, right? Now the third point he said is that in certain crystals like calcite, tourmaline, these we call as negative crystals. Okay, in such negative crystals, ellipsoid, this is the sphere first I drawed, okay, and now I am drawing the ellipsoid. So this is the optic axis. Okay. Now this is for calcite crystals. This is sphere for ordinary wavefront, ellipsoid for extraordinary wavefront. So ellipsoid will be outside the sphere. Ellipsoid lies outside the sphere. So velocity of extraordinary wavefront will be greater than velocity of ordinary wavefront, because this is outside. So it travels with far more velocity compared to this sphere's velocity. Right? Now in fourth point he said that in certain crystals such as quartz, which we call them as positive crystals, if this is the optic axis, now sphere will lie outside the ellipsoid. This is ellipsoid for extraordinary ray, and the sphere will lie outside. Right? This is ordinary wavefront. The sphere lies outside the ellipsoid for positive crystals. So in this, V0 will be greater than V, because this is outside. So it travels with more velocity compared to the ellipsoid, the wavefront formed due to extraordinary rays. So V0 will be greater than V in such cases. Okay. So these are the 4 points said by Huygens. If you like my videos, subscribe it, like it. Stay with my channel Reshma Physics. Thank you.